Alright folks, in this video what we're going to do is talk about how to convert finite automata into regular expressions. Now, in the last video we converted NFAs to DFAs, which is part of Kleene's theorem. We also need to show that any regular expression can be turned into a finite automata, and we also need to show that any finite automata can be turned into a regular expression. The RE to FA construction is pretty well laid out in most theory of comp books. So I'm going to focus on some RIPS stuff that is maybe a little harder, and that will be the last piece of our Kleene theorem that we kind of show out in video, I think. So this is the finite automata to regular expression video. So let's start by looking at a sample finite automata. So this finite automata is an even number of zeros. Actually, wait, it's an odd number of zeros ending in a 1. So any string that is an odd number of zeros that ends in a 1 matches this language. So we could have something like 0, 1. Well, look at that. 0, 1. We could have 0, 0, 0, 1. We could have 0, 0, 0, 0, 0, 1. That's not a fantastically incredible language, but I thought it would be a good language to start with because it is easy to write a regular expression for, and we can then see what happens when we do this regular expression conversion. So the regular expression for this might look something like this, which is 0 followed by some number of even zeros followed by 1. So this forces us to have an odd number of zeros and then a 1 at the very end. So let's walk through the process of how we actually construct a regular expression from a finite automata in a more rigorous way, and we'll start that now. We'll start that here. So let me draw my line for where you guys can't see anymore, somewhere around there. All right, so the first thing we want to do is create a new start state and a new end state. Now what's special about these new start and end states is that they only have transitions away for the start state, and they only have transitions towards for the end state, which prevents loops in the start and the accept state. Now it turns out our start state did have kind of a loop going through it, but our end state didn't. We're still going to construct a new start and end state every single time. Now, the start state should have an empty string transition to it from the start state should have an empty string transition from it to the old start state, and the accept state should have empty transitions to it from all of the old accept states. In this case, there was only one old accept state, so it's going to have an empty string transition to it. Everything else has all of the same transitions that it used to have. There is kind of this hidden rule that you could have null transitions. We're going to kind of ignore that and try to lean on intuition a little bit more. This is called a GNFA, or it will be called a GNFA. Right now it just looks like an NFA, and it really is. This is going to be a GNFA because we're going to allow regular expressions on our transitions. Okay, what we do at this point is we take this, which is definitely the same machine as we had before, and we are going to rip out of it different states, replacing labels with regular expressions. Okay, so I'm going to first rip out C because it's kind of standing alone and it doesn't really have any loops associated with it. And what I'm going to do is kind of rewrite the rest of my machine here, but then I'm going to delete C, and I'm going to replace anything that was involved with C with new transitions. So in this case, the only states involved with C are B and E. And what I'm going to do is I'm going to rewrite the transition from B to E that goes through C as a new thing. And in this case, it's going to be I'm just going to write it as a 1, but I want to kind of tell you how I get to the 1. So the 1 is the transition from B to C, and then we think about the transition from C to itself, which is null, and we star that. Null star is the same as an empty string because it means we take it 0 times. And then there's a transition from C to E, which is the empty string. And so when we put these three things together, they just give us a 1. Now I think you can look at that and say, okay, that's 1. But I think you'll find that kind of thinking through this process in its completion is helpful when we do RIPS later on. Okay, let me draw my line back down here again. Make sure you can always see everything that I'm writing. So now we have a new machine. This machine is the same language as the old one. it doesn't really look much different. And in fact, perhaps all we did is kind of delete one of the steps we took by adding the end state anyway. So let's rip something else. Let's rip the B state. So we're going to start off by writing all of the old states that we used to have. Here we go. And now we have to talk about all of the states that B was involved in and figure out what happens. Okay? The states that B were involved in include A and E. So let's talk about, is there a new transition from A to E that happened because of B? And the answer is yes. I could have done 0 followed by 1 to go from A directly to E through B. Now again, if I'm thinking through these steps, I'm thinking A to B is a 0, B back to itself is a null star, which is just an empty string, and then B to E was a 1, and so when I concatenate these things together, I just get 0, 1. Now, we're going to get null star a lot in this particular setup, but that's okay. Well, at least we get it twice. All right, so now let's look at A. Is there any, we did A to E, but another thing we have to think about, is there any new way to A through B? And the answer is, yeah, A could have gone back to itself through B. Okay? And that transition from A to itself is just 0, 0. I take the 0 from A to B, and then the 0 from B to A. And so, again, if we think about all of those things, A to B was a 0, B to itself was a null star, and then B to A was a 0. Concatenate this together, and we get 0, 0, right? So that's where this 0, 0 comes from. All right, so now we have this new machine. This new machine is just a start state, an empty string, A going back to itself on 0, 0, and then a 0, 1. And this, you can really see that this is a GNFA now and not just an FA, because it has this these regular expressions. This 0, 0 is not 0, 0. It means 2 zeros in a row. All right, we only have one more state to rip, and that's the A. And when we're done, we should be left with an arrow from the start to the end that has a regular expression sitting on it right here. Okay? To go from the start to the end, we take empty string, we think about A back to itself starred, which is 0, 0 star, and then we think about A to E. So this is S to A to E, and A to E is 0, 1. And so the regular expression that we're going to write here is 0, 0 star, 0, 1. And you'll notice this is a different regular expression than the one we had come up with, and yet it describes the same language. This is the set of all odd numbers of zeros followed by a 1. They just did the even starred first, which would lead to different finite automata too. But that's okay as well. There are an infinite number of finite automata for any language. We can always add another state that does pretty much nothing. So that is always possible. And this is a valid regular expression. And this is how we get to it through rips. Let's do one more. Let's do one more that has a little more looping back on itself, and perhaps does something a little more interesting. Let's start with let's do a language that is contains 0, 1. Or how about a string that contains at least 2 zeros, and I'll draw it as an FA like this. This is a string that contains at least 2 zeros. Okay, let me draw my line here. It's close. A string that contains at least 2 zeros. It might look something like this. This is not incredibly simplified. And then what we're going to do is we're going to rip these states out using our rip construction to come up with a regular expression for this. All right, so the first thing we do is we make a start state that has an empty string transition to the old start state. We're going to redraw all these states. Let's label them A, B, C. And you know what? That's not actually an accept state anymore, because the only accept state is the new end state that we're going to create, which has an empty string transition to it from all the old accept states. And then we just rip stuff out. So I'm going to rip B out first. States involved with B include A and C. I will say that when we get to this point and you're writing 0, 1, we should probably replace all of those 0, 1s with regular expressions. and those regular expressions look like 0 or 1, right? Because you can take 0 or 1 to make that transition. So I'm going to go ahead and rewrite those. All right, so now here's our question. Is there any new way to get from A to C through B? And the answer is yes. It looks like 0, 0 or 1 star, 0. So we take this starred. The only time you star anything is when you're ripping out a loop of something back to itself, right? So we consider A to B, B to itself starred, and then B to C. So that's what that expression looks like. We consider A back to itself through B. There are none of those transitions because B to A is null. We consider C back to itself through B. There are none of those because C back to B, C to B in the first place is null. So this is it. And then we can rip these other states out. So let's rip out A. So if we do that, we're going to have a transition from S to C, which looks like empty string followed by 0 or 1 star. Empty string 0 or 1 star followed by whatever was on that transition before. And then we can rip out C, which is just going to be this expression followed by 0 or 1 star followed by empty string. Okay? And that'll be our answer. And I feel like this matches the kind of automata that I had drawn as well. So this is the regular expression that matches that automata, which is you can do anything you want as long as there are 2 zeros somewhere tucked into your expression. And that's kind of exactly how I had drawn that in FA. Sometimes it can be helpful as you're thinking about this to always consider every pair of states, okay? And there's always this situation when you're looking at these states where I want to consider all states like from A to B that involve rip. So there has to be a transition from A to rip and a transition from rip back to B. And this can include itself, and this situation didn't come up for us, but if A already had a transition to B and there was a new process from A to B, then these things are ORed together. So let's say there was a 0 here, a 1 here, a 2 here, and a 3 here. So let's leave the binary behind so that I can just show you something real quick. In this situation, if I'm ripping out this rip state, the new label between A and B is going to be 0, or the new pathway that just got instructed from the rip, which is 1 to rip, rip back to itself star, rip to B. Right? So you get this. There's 2 ways from A to B now. I can either take 0 directly, or I can go through rip. And it's useful to think of this. Now, this also is the same as if we're thinking about A back to itself when we're ripping. So I'm gonna label these in the same way. Okay? So I've got A to rip here, and I'm ripping out this rip state. When I do this, I'm going to get a new label on A back to itself, which is 1 or 2, 3 star 4, like this. So it's kind of complicated. So it turns out that it doesn't matter what you're ripping out, but you can take any single finite automata, and we've done, I guess, 2 of them here. You can add a new start and end state and start ripping out states, and as long as you rip them out correctly, you'll end up with the regular expression that corresponds to that finite automata. And if we formalize this, this would prove that every finite automata has a regular expression, which means that regular expressions are at least as expressive as finite automata, which is critical for Kleene's theorem. I mean, it's one of the critical steps anyway. Okay, that is all we have for today. Hopefully you guys are ready to challenge yourselves and do a few rips yourselves. This can get incredibly messy, but it is also incredibly useful. So I hope you're inspired by this. All right, that's it for today. Take it easy. See you guys next time. Bye.